welcome everyone to the morning session. And today we start the session on post-correlation signal processing, big data in AI, and that's the whole day here. And before we begin, I'd like to acknowledge traditional owners of the lands we're meeting on today, and that's Gadigal people of our nation. And the first speaker for today is Sam Loy from CSIRO, and he will talk about direct image reconstruction using closure quantities for VLBI.
Yeah, okay.
And I'll give you a word for 2 minutes before the question time.
Yeah, sounds good. Thank you. Hello, everyone. First of all, oops, sorry, let's put this somewhere. Congratulations on making it here on a Friday, early in the morning. It's raining again. So I didn't expect a massive turnout or anything, but pat yourselves on the back for making it here to the conference. And so, as a means of a quick self-introduction, I'm Samuel Lai. I'm a postdoc at CSIRO, Australia's National Science Agency. I'm currently based in Western Australia, and my work has to do with image reconstruction, but doing it with machine learning and with closure terms. And so my collaborators in Western Australia are Nithyanandan Thagarajan, Ivy Wong, and Theobos, who's from Data 61. So I have the privilege that my project is fairly simple to motivate. So everyone remembers the 2019 image of M87, the first image of the black hole shadow. But what they perhaps don't emphasize as much is that there were 4 independent teams within that HTC collaboration that did the image reconstruction. And these were the results from the 4 different teams using different algorithms, using the same data products, with regularized maximum likelihood methods and also with the traditional clean. And the images are very similar, but you'll notice that they're not exactly the same. And so you might wonder, okay, why is this important? They're pretty perceptually identical anyway. Well, the thing is, the devil is always in the details, right? So a couple of days ago, there was a talk by Satoshi, I think, who was from the HT collaboration. And he mentioned that actually the position angle of the brightest hotspot has something to do with whether the accretion disk and the black hole spin axis were aligned. If you do your clean based on those, and you really have to calibrate correctly, otherwise your image will be really sensitive to your calibration and assumptions that you have put in during calibration process. But there are certain special constructions of these visibilities called closure phases and closure amplitudes, where if you combine visibilities in these certain ways, then you cancel out the multiplicative phase terms and the amplitude gain terms. And these are called in the triads, they are called the traditional closure phases, and in the quadrilaterals and closed quadrilateral loops, they're called the closure amplitudes. And in 2022, Nithya from CSIRO published a paper on these closure invariants, what he's calling closure invariants, which basically capture the exact same information as both the closure phases and the closure amplitudes together, but constructed on triangular loops only. And so this is a very useful and simplification and generalized formalism for all of these closure quantities. And so he has a package on GitHub, and for the machine learning enthusiasts with us, which I'm sure is all of you, we have a PyTorch implementation as well, so that preserves the gradient graph if you're interested in that. And so this is an inverse problem, right? We have these closure quantities, a complete independent set of closure quantities, and we want to make an image out of them. But if you imagine what they actually represent, they're really a combination of a bunch of Fourier terms. So it's really hard to intuitively understand what each closure invariance does to an image. So doing this sort of imaging from closure invariance directly is an ill-posed inverse problem. And so for that, we want to rely on ML to do this inverse transformation. Okay, so I actually have 2 papers. Originally, when I submitted the abstract for this conference, it was going to be on paper 1. But in the meantime, we've made a lot of advancements, so I'm going to be talking about paper 2, essentially. And paper 1, if I had to summarize, is basically a vision transformer image reconstruction architecture. And paper 2 is using conditional diffusion. And do share one component there that I've highlighted. It's actually, they have the exact same autoencoder, a trained autoencoder inside the network. Okay, so a quick introduction to generative direct. This is also fairly easy to explain because most of you probably have played with some sort of image generation model, textually conditioned image generation model. So you put in a natural language prompt like a cat in a hat or something like that, and it spits out, n number of images of cats and hats. And so that's what's called a textually conditioned latent diffusion model. So the main what is it, innovation, I could say, is that what if we took this model and we made it a closure conditioned or interferometric measurable conditioned latent diffusion model? And so you might know that these diffusion models are UNets, which are expanding and contracting pathways of convolutional layers with ResNet connections in between. And what we've done was we added these attention layers, cross attention layers, in order to perform the cross attention mechanism with the closure invariance. And so if you were anything like me, maybe 1.5 or 2 years ago, you probably understand all those words, but if all those words are put together, what does that actually mean, right? So what I've done is I've reframed the whole objective of the generative direct in the language of Bayesian statistics, which probably more of you are familiar with. So the main goal is to approximate the conditional probability distribution called the posterior. So it's the probability distribution of X, which is the images, condition on Y, which is the measurement. And by Bayes' theorem, we know that this is proportional to the prior, which for us, the prior is from the training data set. And a training data set is mostly of natural images with simple shapes added on as well. And then also multiplied by the likelihood, which is the given by the forward modeling of the observation. So we can learn the probability distribution and approximate this probability distribution with a neural network deep learning architecture and by optimizing this below objective, which this objective just means that it learns the noise applied at every time step. It learns to predict that noise and denoise the whole image, or in this case, it's the latents from pure noise back to an image. So imagine it started off in this location, and then through many random steps, it's now over here. And then by optimizing by this objective, what this means is that it learns to go back to this location. And of course, if the collision variants are something else, maybe the original location is somewhere up here, then I'll just go back to there. That's what that does. So it finds this sort of subspace in the entire closure invariance or latent parameter space that is consistent with closure invariance. Okay, so again, on our architecture, I've talked about what the diffusion model means, the diffusion model of this part, and that gives us a sample of images. And what we do next is that we have to understand that these conditional diffusion models don't actually minimize by the data terms explicitly. So we apply an extra, just append a CNN on top of it, so to optimize for the data term loss. So that's what that is. This fancy C here just means the forward transformation between the image and to the collision variance. So just minimize the collision variance loss to the chi-square. Okay, so now let's just walk us through what this process does. Let's say we have an image that's this crescent over here, and then we do the forward transformation to the collision variance, and we put this into a trained diffusion, a conditional diffusion model. So it starts off from pure noise. Here, just skip to step 500, and then after all 1,000 iterations, it becomes a posterior sample of crescents, which all have different sort of high frequency features. And then you can do this with any sort of morphology. You don't have to retrain it. You just put in a new image, and then it'll create a new posterior sample. And from these posterior samples, you can do this part, which is the CNN refinement technique that I talked about just now. And so this is supposed to be a video, but this is a PDF, so sorry you don't get a video today. But it eventually ends up being a better reconstruction that also abides by the data terms, is consistent with the data terms. Okay, so on the left-hand side, you can see a bunch of trained images. On the top, you see the truth image, and the middle is the gen-direct reconstruction. And you can see that perform very well on both image metrics and data metrics. And on the right-hand side, we have examples of untrained classes, and including Einstein space, which gen-direct model continues to perform very well on. Okay, so we tested it against noise, and we found that as long as the median signal to noise on the collision invariance is above about 3, we still continue to perform pretty well based on our own noise models. And we also tested the generative diversity and put out some images in the paper that sort of speak to the in terms of all the reconstructions that are obtained or what it would have has actually changed. So you can see that there's this sort of 1 pixel wide width. So assume that this is our black hole image, then we can get the width of the black hole shadow correct to about plus or minus 1 pixel, which is in this scale is about 3 micro arcsecond. If you know, put in the location of M87 and everything. Okay, so everything I've shown so far is with our own aperture synthesis code. And so what we wanted to do was to make sure that we validate on someone else's data. So in this case, we chose to perform the NGHD analysis challenge, which is detailed in this paper. And that has 8 UV fits datasets, so 8 different samplings on the UV plane. So this is going to be a different aperture synthesis code, different source models, different noise models. We don't know how their noise was manifested, and they have a varied UV coverage. And so in the middle here, you see that they have 2 ground truth models. There's the M87 on the left and Sagittarius A-star on right. And we have independent reconstructions from, this is taken directly from the Roloff's paper. These are just a different individual who's done the reconstructions with, in this case, it's EHTM code. And so here's how we do. On the top is our M87 reconstruction with GenDirect. And on the bottom is our Sagittarius A-star reconstruction. Again, I've put in independent reconstructions on the right-hand side to see that they're fairly consistent. And not only are they qualitatively consistent, but we've also looked at data metrics. So on the left 3 metrics, if you look here on the plot, are data metrics, and right 3 here are image metrics. And if I just highlight the best performing in each category, you can see that on M87 we perform pretty well on data metrics, but perhaps not the best on image metrics, but still competitive. And moreover, on the Sagittarius A-star, we actually perform the best in almost all categories. And this is mainly because our reconstruction is limited to a more compact region, and the M87, the presence of the jet, actually makes the reconstruction a bit more difficult. Okay, so in terms of scalability, we have demonstrated to some difficulty that this method is scalable to different fields of view and also different resolutions as well. Okay, so as a quick summary, we have shown that generative conditional diffusion and the CNN directly predicts images from a set of closure invariants, or in fact, it doesn't have to be closure invariants, it could be any interferometric measurable. We use closure invariants because they're more robust against noise. And they are trained on noiseless synthetic data, but they are quite robust to noise anyway, with performance that's pretty well down to a single noise of about 3. And they're pretty comparable to other algorithms on the NGHD challenge dataset. Okay, so the paper is under review, so stay tuned for the paper in PASA. And we're also doing a lot of validation right now to make sure that we're very confident in our models before we completely unblind on the UHD public data, both the 2017 and the 2018 data. Okay, so that's it. So I'm happy to take any questions.
Please use the microphone for the questions.
Fantastic talk, Samuel. Thank you. I wonder if you've thought about different things that this might be applied to. I mean, obviously the EHT is a good one. But for instance, just throw this out there, we're looking at MWA data on the sun. It's extremely high signal to noise. Our aim is to get a very, very high dynamic range. We really struggle to calibrate using the sun as a self-calibration source because we have very little knowledge a priori of what its structure actually is. So we have this very, very long iterative process to get from the visibilities to the image. It does work, but it takes a long time. So I'm wondering, first of all, whether you can, off the top of your head, think of any reason why this wouldn't be a good approach. And secondly, give us some idea of what the performance might be.
Yeah, so that's a great question. Behind the scenes, before we unblind on the EHD public data, we've actually unblinded, in a sense, on other data, LBA data. Specifically, actually, I'm not sure I'm supposed to reveal it, sorry. But but yeah, we have tried it on other data, and the result continues to be consistent with more traditional methods and with HCM and other regularized maximum likelihood methods. So it's been pretty reliable so far from our tests. And the main disadvantage, which I'm sure you were getting at, is that with a different UV sampling, with a different observation, you have to retrain the diffusion model. Retraining that is about 10 hours on a pretty powerful GPU that SIRO employees we have access to. And so it's computationally expensive. We have been working on more sampling agnostic, or perhaps instruments. It's for a particular instrument specific, but sampling agnostic methods. So this is sort of the direction we're moving towards after we finish up on this whole HT challenge.
Yeah, I mean, the NWA has such good UV coverage.
Mhm.
You may find that once you've done it once, you've got all of the information you need to process any other observation, regardless of the hour angle of the sun.
Yeah.
Great, fantastic talk. Thank you.
Thanks for that.
Thanks, Sam. Just a quick question. You have plans to extend it to do something like multi-frequency synthesis and polarization, perhaps?
Yeah, so definitely polarization, I think, is coming first. The main reason for that is because we've had people from the Ishi communicate with us, and in terms of scientific value, having a very good, reliable sampling of the posterior in terms of like a polarized image is more useful for physics than things like dynamics. Multi-frequency, multi-frequency is also something that we're thinking of doing. I mean, HT is basically the observations are 230 and 345 gigahertz these days. So multi-frequency methods have been the best performing so far, even on the NGHT analysis challenge. And so that's something we're thinking of doing, but maybe it's a little bit further down the line. It's maybe after polarization.
Thank you. So maybe one more quick question. Yeah.
The signal to noise of 3, to push that, I mean, you're training on completely noiseless data. To push that down, you just start training on noisy data? Or what's the approach?
So no, it's still actually trained on the noiseless data. So it's the performance of the model.
Yeah,
So
I mean, if you wanted to improve that signal,
okay. Sorry, I misunderstood the question. But yes, that is something we have tried, and it turns out that when I train on noisy data, that when I'm training the diffusion model, we have issues with convergence. But that might just be the early experiments didn't work, and maybe there's a better way to go about it. But I mean, in the paper, that's what we said, that it's possible to do, to train on noisy data. But in practice, our early experiments showed that we had some issues. But certainly that's something to explore further and then continue to talk after.
Thank you. Let's thank Sam again. So the next speaker is Brian Kirk from New Mexico Tech, and he will tell us about the reinforcement learning for radio interferometry data processing.
All right, thanks everyone for coming this morning. As Max said, I'm Brian Kirk. I'm down in New Mexico Tech and in Socorro, and I work with Urvashi Rao and Ramya from New Mexico Tech. I'll be talking to you about radio interferometry and NRA's instruments. As most of you already know, radio interferometry allows us to image the invisible. The arrays sample the Fourier space, which can then be inverse Fourier transformed to make an image. And if any of you have done this in practice, it's not that simple. There's a lot of algorithmic decisions to make and along the way, which affects the results and the science along with it, at least until we all switch to closure phase. NREO operates multiple interferometers. They have the VLA and the VLBA in the US. They co-manage ALMA in Chile, and then soon there'll be the NGVLA. These are general purpose instruments with many use cases, but there's blessings and curses to being general purpose. And one of those is, how do you create pipelines for a general purpose instrument? Domain experts spend design these automated pipelines to offer enriched data products to the end users and the researchers and the community. The two red flags with this is that creating a pipeline is a resource-intensive task. So not every science use case gets its own optimized pipeline. And what happens is usually you get a one size fits most or a one size fits many that's then applied to all data sets. The issue is that if you have a generic pipeline, you kind of get generic results. And then you have internal teams of staff that do quality assurance, or you have the end user who's working on their science, review the output, make data set specific changes, and then rerun scripts for better results. And this is kind of what we want to address with reinforcement learning. And then as a very brief overview of the main flavors of machine learning, you have supervised learning, which requires labeled data. And this learning algorithm basically mapped from X to Y. You have unsupervised learning, which the advantage here is that you don't require labeled data, and the algorithm underneath learns the underlying structures in your data set. And then you have reinforcement learning, where an agent interacts with an environment and it learns the mapping of ideal states and actions. Just to note that these are learning algorithms. Architectures are neural nets, CNNs, ResNets, transformers, all that kind of stuff. Those are the architectures in which you implement the learning algorithms. And then taking it one step further, deep reinforcement learning is just adding neural nets onto your reinforcement learning algorithm. So the main pillars here are that you have an agent that explores random state and action combinations. And then over time, what you do is you actually cool down that randomness, which is essentially needed to stay out of local minima. And then that information is then passed to the neural nets, which take all of that sampled state and action information and essentially build up a loss landscape. With the idea being that once you have a loss landscape, then an agent can traverse that landscape with minimal loss. How we envision using this for post-processing is CASA, which is the main software library for the VLA and ALMA. We can use the CASA functions as actions that the agent is able to play with. The dataset properties, whether they're statistical or image-based, this is actually the information that forms the state that the agent can play in. Then the agent explores to learn the loss landscape, with the idea being that depending on what you want out of the data set, you will get a different custom path to that objective. That would be better than just some generic directions or recipe that you would follow. So how we think this can help is that right now the domain experts spend lots of time exploring sequences and settings for tasks to work for all or most data sets. Here, using RL, we can actually move the exploration to the machines, which scale a whole lot better than domain experts. The other idea is that staff and end users spend a lot of time optimizing generic scripts to their specific data set needs. Here, we can also see that RL, once you know the loss landscape, then you can use an ideal path to get through, based on your specific data set properties. So true data-driven processing. And this all sounds good in theory, but what happens if we actually test it? So one of the things we wanted to test it on was a very specific problem in calibration, which is how much averaging, if any, do you apply to your data set if you want to remove gain distortions? So essentially, calibration accuracy depends on the signal to noise ratio of the calibrator data. And the challenge is that you can average over the time and frequency axis to boost signal to noise and reduce the number of points to reduce computational load. But the problem is that if you average too much or in the wrong axis, you will actually obscure the distortions you want to divide out and remove from your data set. So the initial test that we gave to the agent was, can it learn which axis to average based on the data set and then make the decision between the trade-off between calibration fidelity and the runtime. And then on the top row here is just a simple example of if you average across the right axis, you reduce the number of points while preserving the signal that you want to divide out. If you divide it out, model it correctly and divide it out, you're left with nothing but noise. And the idea is there that then your sine signal is the only thing left. If you average across the wrong axis, there's really not much that you can model and then divide out, leaving you with a poor calibration. So the first test was in short, can the agent learn to transform something like this into something like this? Which axis should be averaged, if any? And to do this, we actually created hundreds of simulations like this, and we varied the gain signals in different axes and different signal to noise ratios. And then this is the environment that we let the agent play in. So the objective that we gave it was, can it achieve noise, ideal noise in the distribution, ideal noise distribution in the residuals? The simulations we gave it had a point source at the phase center. We added gains and then noise. And then the three features that we used from these data sets was just the mean gain, the frequency standard deviation, and the time standard deviation. And then we gave it 5 actions that it could play with, which is essentially an action for each axis that it could average across, plus a few combinations. So it could average frequency, time, it could average both axes, average across neither axes, or do nothing. And all of these actions were actually built on CASA's apply cal and gain cal tasks. And then what we used as feedback to the agent was this earth mover's distance, measure the distance between the distribution of the theoretical residual noise and what was actually achieved. So here's just a visual example of what that might look like. If this is our single simulation, if you pick the correct axis to average across, you model this gain waveform properly, divide it out, you're left with nothing but noise. The theoretical distribution and what you actually achieved is quite close. If you pick the wrong axis, you have a bunch of gain residuals left over, you have a bunch of junk in your residual image, and your distributions are very different, which actually forms the penalty value that is given back to the agent to say, hey, that was a bad choice for that simulation. You'll notice in this first row and this last row, these are 2 different actions, but the imaging results are actually the same, or very close to being the same. The only difference here is this action, which was no averaging applied, actually took 50 times longer in runtime. So this is the type of stuff that we would really like to avoid in operations. If you can get the same imaging quality with, the 50% or 50 times speed up, we'd really like to pick that one. So coming back, what did the agent learn? What you're seeing here in this graph is all of the dots here indicate a different simulation with different properties. So what we saw in that last slide, this simulation is essentially 1 dot in this plot. And these are all the sims that we made that we fed to the agent to play with. The color that you're seeing here is what the agent learned to do, or what the agent found was ideal to do for that given simulation. And you'll see here that there's very obvious regions that it found. It's not the cleanest, but too many points and you don't get to see much. Essentially, you have regions, and these regions are kind of dirt simple, very obvious. When you have low frequency standard deviation, you should average the frequency axis and apply calibration. If you have low time standard deviation, you should average the time axis and so on. And it turns out that these regions match up with domain expectations. And we took it a step further than just match domain expectations or intuition. We actually brute forced every possible action for all of the sims just to get a ground truth, just to make sure, and it matches. So the second test we gave it was, okay, it can pick an ideal action. Can it actually learn a sequence of something? And what we did for this is we added antenna-based RFI to our simulations, and the challenge to the agent was, can you go from this to this? And you can have multiple actions if you want. The trick here was that the ideal sequence, or if you want to get to a global minimum, you actually need to flag first before applying calibration. So this is opposite to a greedy approach, which is a greedy approach would take the largest change first and then continue on that way. This actually, if you calibrate first but leave the RFI in, your gain calibration is going to be distorted, and then you won't properly remove the signal, and you'll have residuals left over in your image. So this is our attempt to trick the agent. Essentially, it had to learn through exploration and trial and error to figure out the correct sequence. And to do this, we adapted what we gave it before. The simulations now had RFI in them. We gave it an extra input feature from the simulation, which was just what the max value was. And then we gave it an additional action that it could play with, which was flag. And this was based on Casa's R-flag algorithm. And in short, it solved the sequence for many different initial conditions. For this, we actually used a deep Q network, which is a form of implementing deep reinforcement learning. But the neat part about this is that the agent only used 1% of all the simulations we made. So about 50 simulations it was able to play with to build up its learning of the loss landscape. That loss landscape was then used and applied across 5,000 unseen data sets, which it was actually able to solve correctly for 90% of them without seeing most of them. So that's the achievement and the kind of the scale up that we like to see. We do recognize that this is possible because this is a fairly simple space. We don't expect it to be this easy going forward as we reach full complexity. But another nice part of this is that because we have such a simple space that you can divide with hyperplanes, you can actually use a decision tree classifier to actually get out human interpretable boundaries for this. So you could hand a domain expert, here's the table, here's what the agent is using to decide, does this make any sense? Is it doing nonsense? And so on. A pleasant side quest, we actually swapped out, there's two main automatic flagging algorithms in Casa. One is R-flag, the other one's called TF-crop. We wanted to just swap out the algorithms to see what the agent would do. And essentially, without doing any hard coding or telling it what to do, we just let it play, and it figured out in this situation, there's two spikes of RFI. One is kind of sitting in the trough of the gain signal. What it did is it flagged and removed the highest outlier, but then it couldn't get the second one. So what it decided to do is calibrate here, which then changed the prominence of the remaining piece of RFI, and then it decided to flag again before stopping. So we didn't tell it to take 5 steps. We didn't tell it to take 4 steps. We didn't tell it to do interleaving flagging. It figured out how to do this all on its own. So this was a very nice example of data-driven processing. And then the third test we gave it was we wanted to make sure that it could do loops. And loops are important for us because we use self-cal a lot. If anyone's not familiar, self-cal is just a bootstrapping method in which you use your actual target as its own calibrator, in which you iteratively refine the sky model to derive better calibration solutions. And for this one, what we did is we added a second point source off center. We gave it another feature to look at, which is told it whether there was 1 or 2 sources in the simulation, and then we gave it 10 actions to choose from. Essentially, these first 4 with an additional model deconvolution step in front. And then the agent actually was able to perform multiple rounds of self-cal before it decided to stop on its own. And it decided to stop not after some predetermined number of steps, but when the runtime penalty outweighed the image improvement that it was achieving, it decided to stop. This is just neat to see. This is we can also adjust the runtime and image trade-off depending on whatever your compute availability is or how much time you want to spend or waste. The agent was able to stop at a different number of self-cal loops. And then this is just a way of us slowly starting to build up the visual of what this loss landscape actually looks like. So in this top graph here, we actually have the simulation as a node now. If you can see the colors, the connections coming off from there are colored with the different actions and therefore the resulting state of the data that it's in. This is an example here of what it looks like if you were to actually map what the agent is doing. These are the different pathways it's exploring, and it's trying to find the global minimum within here. And then if we were to look for one example, what I learned is this is just 2 rounds of self-cal, and this is the progress that it made in doing this, from transforming something like this to something that's fully noise. This is just one trace of that loss landscape, by the way. These are kind of compute intensive, and we're working on scaling this up, which is what I've been doing the last 2 months. There's this consortium called the OS Pool. It is a bunch of institutions that get together and they share their computing resources for open science. This has allowed us to drop learning and loss landscapes from months down to days. And then essentially using this cluster of clusters, compute is no longer a barrier to research, which is pretty exciting. And just for some quick stats, they have instantaneously at any given moment anywhere between 40 and 50,000 CPU cores available to be used. Just on Thursday of last week, in one day, almost 750,000 CPU core hours were used just in 24 hours. So it's quite impressive. And it turns out it's not just the US, but it's going global. And one of these compute nodes is at Swinburne. Yeah, doing this in progress, running on this right now as we speak. And then the next step and the last bit is we want to do the real data crossover. So we've demonstrated that our agent can learn ideal action selection. It can do sequencing of the appropriate actions, and it can do loops. Our training environment and simulations up until this point kind of mimicked real-world calibrator data sets. And then the idea is that we want to go after the VLA's calibrator surveys, which are repeated about once a month. And right now, how they process that is either someone by hand, Rick might even be doing it by hand, or a very just crude script runs. And this is actually where we want to plug in our agent to see how it performs versus the current methods. And I'll leave you with that. Thanks.
Have time for probably one question. Okay, I'll ask. So do you expect, like, when we have to deal with real data, that's obviously a big challenge because you can find something which wasn't like in any model or anything, some kind of strange artifact or something.
Yep.
Do you expect, like, how do you expect this particular system will behave? By the way, I was very impressed that it actually could make the decision to do flagging twice, because that's what we often do when we do data processing.
We were surprised too. I would say it depends on how thorough your training is beforehand. But if you find something out of distribution, we expect essentially the agent won't really know what to do with that scenario, and it will try to map whatever it does know as well as possible to the out of distribution scenario. So I would anticipate something going a little haywire. Hopefully the idea would be is that it would be very obvious to the human that something has gone wrong, and you should probably look at what it's doing. That's the best I can give you right now.
Yeah. Thank you. Let's thank Brian again. And the next talk will be by Kamsala, who will be filling for Vikram Rani, and the talk is on DSA 2000 and data generation and products of the DSA 2000 radar camera.
Right, good morning. I am going to do my best to do justice to both Vikram and to you in this talk, but I feel like it's almost inevitable that you will come up with some questions that I would have to refer to him at the end. So the DSA 2000 is, I think, an ambitious project. This is what it looks like: 1,650 antennas, each 6.15 meters diameter. For those who've seen these talks in the past, it's been adjusted. We've gone through a re-optimization exercise. And that gives us a 1.6 Jansky system equivalent flux density at zenith. The array is planned to be deployed in Spring Valley, Nevada. It's a pretty remote area. And we have re-optimized the beam to achieve slightly over 3 arc seconds resolution. And at that site, we can access declinations above -38 degrees. We'll have simultaneous coverage, 0.72 gigahertz, and we plan to run a series of commensal surveys starting in approximately 2029. And we have, in terms of processing, we have two flavors of it. And the one we've called a radio camera. I'll speak a little bit more about that. And the other one is a chronoscope. And they split between imaging and time domain, as you might judge from the names. And I think something that we keep emphasizing is that our data will be public. So there's no proprietary period. And as soon as we can ascertain the quality of it, it will be available for everyone. And the DSI 2000 fits into this broad category of survey instruments that are either online now or coming online in this decade. So it's a natural fit in this community of instruments. And we like to quote yet another quotable quote from Matthew Bales, who said that the DSI 2000 can keep all radio astronomers worldwide busy for a decade. And we certainly will hope to do that. The survey science falls into these 4 broad categories. Underneath that, we have 8 key science goals. There's plenty more detail there. But the instrument was optimized for survey speed for this reason, while still maintaining sensitivity. So there's a little bit of balance there, but survey speed is the ultimate goal. And using that, here are some forecast numbers. So 1 billion new radio sources, 10 million galaxies, 10 to the 5 FRBs, 20,000 new pulsars, so on and so on. So these are big numbers and enabled by this emphasis on the survey speed. And so what that might look like in a survey is split up here. So you get the cadenced all-sky survey taking up the bulk of the time. And that is variable in depth and cadence. So it's sort of adjusted on the fly, but every individual pointing will be about 21 minutes. And the tiles, that's tiled into 72 square degree tiles. Like I said, these surveys all run continuously and commensally. So every 21 minutes, there's a set of images produced. There's a breakdown of what they look like. So the continuum images in 10 spectral windows, and then various different spectral resolutions, and the polarization images in 500 channels. And then the chronoscope will perform fast radio burst search and pulsar search. And excuse me, the pulsar timing will then follow up and time pulsars using 4 beams with coherent dispersion. And finally, that data then goes into the public archive. At this point, the baseline is to have that managed by IPAC. And again, no proprietary period. And we are considering other alternatives here, so migration to a science platform and so on. So the reason we need a radio camera is kind of captured in this slide. So when we look at the data rates coming in from the antennas, it's 200 terabits per second. So that's still pretty challenging. And we can't really process all of that. And even if you look at that post correlation, it's still too much to store the visibilities. So we need to produce images on the fly that are good enough so that we can discard visibilities. And that obviously is something that makes everyone a little bit nervous. So we have to get rid of this iterative loop of processing and reprocessing data to get the image quality up. So looping back on the data rates, the initial antenna data rate here, 200 terabits per second. The red dashed line here is actually the boundary between what happens in Spring Valley, so local to the array, and what is processed in a processing facility in the nearest town called Ely, which is about 100 kilometers away. So we ship order 40 terabits per second across that 100 kilometers. And then it reduces down to the single digit terabits per second numbers. And then once it's imaged, you get into the order 100 gigabits, which is quite manageable, relatively easy to deal with. So why? This is a typical image as you would produce with the VLA. I don't think I need to go into much detail here. But if you have 2,000 antennas, then the raw image would look much more like that. So that's the aim. And another way to show that is quite popular is to take an image and say, well, guess what that is. And so this is the VLA version. Then you get the Meerkat version. You can see it's a person. Maybe if you know a bit about our history, you can start thinking about who it is. Now with SKA Mid, you can say, oh, that looks like Eric Schmidt. And with the DSI 2000, you get really the full details. So there's no need for visibility-based deconvolution. And the imaging pipeline is deterministic. It's just a streaming pipeline that produces images without any intervention, without any human involvement. So to do that, you need obviously lots of antennas and an optimized array layout. So here's a little summary of how we got to that optimized layout. And the image on the left is basically an ideal layout. So it's circular. And then you progress into the real world, and that looks different. And then, of course, once you've done that, you have to verify all of that. So there are various people involved in this process. So initially, Dave Woody came up with the ideal layout. And then we actually identified the valley and started to establish what is on the ground, what do we need to avoid, where are the streams, where are the roads, where are the parcels of private property, where are the sage grouse, and where there are possibly cultural artifacts or anything else you need to avoid. And so Joshua Albert actually wrote an optimization algorithm that then tries to balance all of the different perspectives whilst avoiding everything that we know about. And that came up then with the final layout. Oh, sorry, that was the wrong way. With this final layout, and you can see there are cutouts here that are due to mountains, that are due to sage grouse, that are due to private properties, all that kind of thing. But the performance is maintained, so that gets you back to what the ideal performance would be. And on the extreme right, you can see several of the performance curves, which were then verified by Ryan Keenan and Vikram himself. So this all then is validated through forward modeling, and the entire design is validated through forward modeling. So we create a model and gradually increase the accuracy of that model by adding everything that we understand, everything we know. And so that models the various different aspects that cause imperfections, and ultimately gets us to what are the requirements for calibration, but also back to validating the antenna requirements, performance requirements. And the antenna requirements, the performance requirements are much more severe than you would expect of an antenna in this frequency range because of that, because we need to maintain the imaging quality. And so this is an example. This is using a Meerkat image. That is the ideal image, and this is the forward modeled image. I actually zoomed into this to try to see the difference, and I couldn't. So it's looking good, but of course, as we progress in the forward modeling, we will increasingly add bits and pieces to it that might have an effect here. And we can also tweak some of those parameters to say, what if the antenna's performance is not actually what we aimed at? What happens? So then moving on to the software design of the radio camera processor, I will not expect you to be able to read the block diagram, but there is a block diagram. It creates images in these various spectral resolutions, and it accepts an input data stream from what we call the radio camera front end. That's an FPGA-based channelizer that's in the Valley. So that then brings the data rate down to about 34 terabits per second. And once it's processed these images, created these images, it drops the data rate down to about 23 gigabytes per second. It uses several frameworks to ease the development and to make it highly scalable. So Legion, Cocos, and there's a whole bunch of things. So the next four bullets are kind of status points. The SimCam is the piece that allows that physical instantiation of the software to run. That is functional, and we use the tensor core correlator from John Romain. That's integrated with pre-calibration flagging. What is happening at the moment is that the calibration code is being integrated into that same framework to test that. And it's obviously all containerized and with all the nice software continuous integration testing. So the relatively newer piece to the radio camera is the chronoscope. So this is the transient processing backend, and it has these two aspects to it. The one is searching, and the other one is to time the pulsars. And looking at that, I'm going to have to speed up a bit. The searches in real time using about a quarter of the band, and then forming many, many beams to tile the entire field of view. And that leads to this expectation of discoveries. I'll jump through quickly. This is the pipeline. Again, block diagram. I can't go into detail. But you can see that with all of these many beams, the data rate jumps up quite dramatically from the input before it then starts to settle down again. And there are some operations per second numbers and so on. And this is then the equivalent of the pulsar pipeline. Jumping from that into hardware, this is the only real hardware slide I have here. This is what's in our shopping cart. For anyone who's building a big instrument, you should probably look at this. This is the NVIDIA NVL72/144 and beyond in the future that was talked about in the GTC 25. So this is the total extent of all of our processing for the radio camera and the chronoscope, 4 racks. They're standard size racks. They're not standard racks. But the compute density in there is huge. So then we've got the images and we've got the folder profiles, etc., and the FRB candidates. Then that gets flown into what we call the DAT subsystem, data processing, and that receives these raw data products and generates the science products from it. It's also still it's not strict real time, but it keeps up with the stream, and it does the quality checking. So this is where we assess whether these images pass muster and whether we can say that an observation has been completed. And it then starts to store data. So this is where we start storing data. The output of the DAT subsystem then feeds the archive, which is offsite. This is what a typical data release might look like. Order 300 terabytes of data split into those different categories as mentioned there. And so to summarize, we use extensive forward modeling to validate the design and the design requirements. We then produce this real-time streaming deterministic imaging pipeline, which is enabled by that design. And the surveys only really become tractable when the radio camera helps us to reduce the output data rate to manageable levels. And then finally, thanks to companies like NVIDIA and AMD, the processing is viable with platforms that are either available now or will be available well in time for our project. Thanks.
Questions? Thank you. Yeah, nice overview. So in the imaging pipeline, you specifically stressed, well, we don't have time to for ourselves to go back to facilities, but we need to stream the data to geographic data. Now, I didn't have the time to digest the entire block diagram, but when I saw, for example, the FRP search block diagram, there seems to be a loop closed. So there are some points that candidate selection and candidate selection was fed back into the pipeline. So there is a loop there.
Yes.
So should that also be a streaming pipeline?
Yeah, so in the imaging pipeline, that just flows through. In those pipelines, there are actually circular buffers that allow you to have smallish loops to get back to data. So it's not strictly all streaming. The chronoscope is a little bit different in the searching. Yeah. Sorry.
Be quick enough to before a certain buffer is overbid, basically.
Yes, I mean it has to be, and again, forward modeling will verify. For example, you could make the circular buffer a little bit bigger and allow yourself a little bit more time, which obviously costs dramatic money at those data rates. So that we're in the process of making sure that we've got all of that verified, that the time is enough.
Thank you. More questions? I'll ask. So in with ASCAP, we of course had very similar idea early on that we'll just process the data on the fly, like no, essentially, well, we plan to have one major cycle, but no iterations over the data again and again. Then of course, greedy astronomers come and say like, no, we need more. So do you expect something like this might happen? Maybe not straight away, but say 10 years down the track?
I think it's almost inevitable. We're in a fortunate position that so far we've been funded by Schmidt Sciences, and they've explicitly said, go and disrupt. And it causes lots of discomfort, but they've been true to their word. When we've disrupted things, they've been very happy about it. We expect that will continue, and we actually have a few things that will probably in the next version of this we'll talk about that are quite disruptive and additions to the telescope. But we've already had the question: what are the upgrades that you would expect to see, for example? So yes, it's inevitable, and our own in-house astronomers keep saying, well, what if we just do this or that? And managing that with the engineering team is challenging because it's things do change, and they change late. One example is that in this year we changed from 2,000 5-meter antennas to 1,656.15 meter antennas. So it's all about optimizing. I mean, that's in the end, from a hardware design perspective, that's a relatively small change, but these kinds of changes happen, yes, and you should expect that.
Thank you. Let's thank Francois again. The next talk is by Peter Koleski, who will tell us about optimization of hyperparameters of STEFCON.
Okay. Hello guys, I am Peter Koleski and I am studying at Stellenbosch University in South Africa, and I will be talking about analysis of optimal hyperparameters for the radio interferometric calibration method STEFCAL. Okay, so here's the team of experts. So I've already introduced myself. Then my supervisor is Trinko Grobler and my co-supervisor is Waldo Kleinhans. Okay, so a radio interferometer is an array of antennas that work together as a single telescope. In radio interferometry, the radio telescope observes and characterizes a celestial object in the radio spectrum. During this observation of the celestial object, errors are introduced into the observed visibilities, and we use calibration to try and solve those errors. So you can see here in this equation here, we try to solve the antenna gains, where D is the observed visibilities and V is the antenna gains multiplied by the model visibilities. So we can use algorithms like Levenberg-Marquardt to solve this complex nonlinear least squares optimization problem. So this is the update step for Levenberg-Marquardt. And you can see in Levenberg-Marquardt, we need to get the inverse of the full Hessian. And that is very computationally expensive. That makes the complexity of Levenberg-Marquardt p to the power of 3. Another algorithm we can use is the alternating direction implicit method, STEF-Cal. So here's the update equation for STEF-Cal. And if you, like you've seen in the previous slide, Levenberg-Marquardt, you can rewrite Levenberg-Marquardt and you can state STEF-Cal in the same sense, where you only take the diagonal Hessian. So then you set lambda in even iterations equal to 1 and in odd iterations to 0, and then you have STEF-Cal. So we use an approximation of the Hessian in this case. Here's another way of describing the update equation of STEF-Cal, where we set lambda equals 0. So getting the inverse of the scaled Hessian, well, the diagonal Hessian is much easier than getting the inverse of the full Hessian. So this makes STEF-Cal p to the power of 2 in complexity. So as we've seen, STEF-Cal has 2 hyperparameters. The first is lambda even equals to 1 and lambda odd equals to 0. So it has been shown that that this 1 and 0 is good hyperparameters, but it's not optimal hyperparameters. Well, it hasn't been proved to be optimal hyperparameters. So we used 2 types of ways to analyze these hyperparameters. First is grid search, and second is particle swarm optimization. So first, grid search. So you have a set of hyperparameters that you want to check the fitness of the algorithm at set points. The main problem of grid search is that it has limited resolution, and it cannot fine-tune these hyperparameters. But the nice thing about grid search is you can check the fitness of the algorithm at specific points, keep it in this grid-like structure, and plot it as a heat map to see the hyperparameter search space. Next, we have a particle swarm optimization, also known as PSO. So we can also use this PSO to do the hyperparameter tuning of other algorithms like the STEF-Cal. And it's continuous hyperparameter, it allows for continuous hyperparameter searching, meaning it's not bound like the grid search. But one of the problems is the PSO itself also has hyperparameters, meaning that there should also be that means that hyperparameter tuning should also be done on the PSO itself. So what we did is we used a variant of the PSO where hyperparameter tuning on the PSO itself is not, you don't have to do hyperparameter tuning. And that PSO is known as the PSO IRCSK. So this is the first result. This is the heat map of STEFCAL. This is for a 4-antenna problem. And during the simulations, we simulated many data sets with different types of errors introduced into the visibilities. So we also saw that over all this different error types, the search space keeps the same structure and where the minimum points lie and so on. And the search space is also static. So yeah, this makes it optimal to use a PSO on this search space to get the minimum. And that's what we did next. So we only used the grid search to get this a picture of the hyperparameter space to get intuitive of how it looks. So then we use the PSO to get the optimal hyperparameters for STEFCAL. And you can see on the diagram on the left, we have lambda odd on the y-axis, lambda even on the x-axis. We plotted the 95% confidence ellipses for the optimal hyperparameters of STEFCAL. DO-STEFCAL stands for dual optimized. And we also plotted the mean of the optimal hyperparameters over all these different type of errors we introduced. So you can see on the red, that's the mean for the red, and we have the confidence ellipse, and it will increase in antenna size. So from red to orange to green to purple, it will increase the antenna size until 256 antennas. So I also did, I zoomed in on this graph here, and you will see as the antenna sizes increase, the optimal hyperparameters tend to 0, 1, which is actually the original STEFCAL as we stated. Okay, next we calculated the flops, and we used the mean iterations to determine how efficient how many flops it will take. And we set STEFCAL to be constant here, and that is the red as a red dashed line on top. And we compared this dual optimized or the optimal STEFCAL to the original STEFCAL. And you can indeed see that the optimal STEFCAL is performing better than STEFCAL. And you can see the flops is decreasing as the antenna sizes are increasing. So here is just a table with a bunch of data. We just wanted to make sure that the solutions we get is good. So we did calculate the standard deviation of the iterations, and we also calculated the mean residual norm of original STEFCAL and the optimal STEFCAL. And in the case of 4, 9, and 16 antennas, you can see for antennas, the mean residual norm was a bit, wasn't as good, but as antennas became more, the mean residual norm was actually better. And that means that we get a good solution when we compare it to STEFCAL. Okay. So, conclusion part 1. Having, optimal STEFCAL, the hyperparameters will tend towards original STEFCAL, which is lambda even equals 1 and lambda odd equals 0. We haven't proven yet that it will definitely converge at 0, 1. It only tends to it. Then when we optimize the hyperparameters, we get faster convergence. And when we leave STEFCAL unoptimized, it will lead in wasted computational time. So we did some more research. This is extended research. We also created a new algorithm called non-diagonal STEFCAL. So what non-diagonal STEFCAL is so we have LM that uses the whole Hessian. We have STEFCAL that uses diagonal Hessian. But we created this non-diagonal STEFCAL that uses a better estimate of the Hessian. So it lies in between LM and STEFCAL. And what we saw here is the math didn't really work out when we set lambda even and odd, or lambda even or lambda odd to 0. So you will see in this graph here on the left, the iterations is very good at 0, but the solution is very bad because the mean residual norm, the maths break when we go to 0. But yeah, so we introduced bounds so that when we run the PSO and so on with this algorithm, it can't go in between it's minus 0.05 and 0.05. So yeah, we just don't let it like walk around there. But you will also see that the search space looks very similar to StefCal. This is the 95% confidence ellipse for the optimized NOS. And you can see it goes to 0 for 4 antennas. It's very near to 0, but it's not on 0. And then it just travels in a different direction, which tells me that it wants to go to 0, but we introduce those bounds. So it's trying to get a better value, a better solution that is not 0. Okay, so here's the mean iterations. This is for StefCal, the optimized StefCal, NOS, and optimal NOS. We saw that we saw that introducing more the constraint, it's not performing as well as StefCal. It did indeed beat StefCal in antennas equal to 4 and 9. And StefCal, after 4 and 9 antennas, as the antennas increase, StefCal outperforms NOS in terms of iterations, mean iterations until convergence. And yeah, so in the next slide, this is just a zoom-in version to actually show you that it beats StefCal when using NOS. So here's the flop analysis for NOS and StefCal. And yeah, so we saw that in the first, we saw that NOS is a very good competitor in terms of iterations. But when we look at the flops, it doesn't compare to StefCal. So conclusion part 2 is, if we can fix the maths for NOS, we will maybe get a better competing algorithm against StefCal. And so if we can fix the maths at lambda even equals 0, lambda even equals lambda odd equals 0, then we will get a algorithm that will converge in less iterations than StefCal. But yeah, it's still not enough to beat StefCal in flops. Thank you.
No questions? Probably missed it, but is the input just simulations, or you took some real data as well?
No, we only did simulations at this point. Yeah.
And have you played with noise and like of different properties? So it was just Gaussian noise, independent, and all visibilities.
Yes, so we introduced different types, amounts of SNR and also maximum amplitude. I think there was 64 different types of sets of errors we introduced, and that's how we calculated the mean of the average iterations and so on.
Will be interesting to add something like RFI or some other things which actually doesn't fit into sort of Gaussian noise model, because you might find that some algorithms are more robust and others are less.
Yeah.
It's yet another angle. So questions? We still have time. Oh well, thanks, Peter.
Okay. Thank you.
And And the next speaker is Devnal. He will tell us about hyperdrive, the new generation calibration software for NWA.
Television. Could I also ask the AV team to just dim the lights so you can see the background? Thanks. So my name's Devnal. I use they, them pronouns, and I'm from the Australian SKA Regional Centre. It's my honour to be able to present to you half a decade of work from a cross-functional collaboration that's managed to deliver a really extraordinary calibration and ionospheric subtraction bit of software. What you see in the background is a little bit of foreshadowing. This is what it looks like when the ionosphere interacts with low frequency radio observations, and spoiler alert, it's not good. So the green button, is it? Great. So the NWA is also known by its Wajiri name, the Fulgramanu, is operated from the Inyana Mane Ugari Bundara, or the CSIRO Murchison Radio Astronomy Observatory. It is co-located with the SKA Low and operates on a similar VHF band, that 80 to 300 megahertz range, of which 30 megahertz or so can be processed at a time. It has a pretty wide field of view at 25 degrees at 150 megahertz. And it's just had a bit of an upgrade. So it can process 256 tiles at a time. And one of its greatest strengths is the 44 or so terabyte archive that has been collected over the last 11 years. So all you need to access this is an NWA ASVO All Sky Virtual Observatory account. So that brings us to the first member of the hyperdrive family, NWA Lib. So that upgrade that I mentioned required a very drastic change to the way that the correlator output format worked. And so that meant that a lot of software needed to be rewritten to handle that change. And so the NWA operations team produced this library to be able to handle both the old and new correlator formats, as well as the voltage dump formats, and some changes were needed to the metadata formats as well. So this is written in Rust. It's been constantly updated by the operations team and has APIs available in Python, C, and Rust. But if you read the raw correlated dumps directly, you're not going to get much out of that. So what you need to do is pre-process that a little bit to get rid of some of the things like interference. So despite the fact that we have a very a world-class radio quiet zone, we still get all kinds of interference from reflections and accidental transmission from aircraft and satellite constellations. It's getting a little bit worse these days, but it's also quite a sensitive instrument in that it can pick up digital TV from all the way from Perth, 800 kilometers away. Depending on the weather conditions, it can duct through the troposphere and cause issues. We also have a bit of a hostile environment. So we have kangaroos and camels that like to go through some of the dipoles and knock them over or crush them. So there's all kinds of serious weather like lightning and so on. So that's why we made the next member, Beely, which does the pre-processing. So it keeps track of the monitor and control system keeps track of dead dipoles and tiles, and Beely is able to flag those. It also uses AO flagger for some RFI flagging. And we are in progress integrating some new RFI algorithms like SINs and evils. So Beely also does the instrument-specific corrections for the NWA, including this new Van Vleck corrections for the legacy correlator. And finally, it does the conversion to the standard radio astronomy file formats like UV-FITS and measurement set V2. And that's all integrated into the NWA ASVO, which is where most people get their visibility. So you usually don't have to run Beely yourself. So even if you've calibrated your data, you're still a bit of a way to go. We do calibration next. So that involves taking a nice accurate instrument model, combining that with a sky model, simulating what the visibilities should look like and solving for the corrections to remove any gain or phase effects that will be imprinted on the signal as it goes through the signal chain. So we typically break this up into direction independent DI and direction dependent calibration DD separately. So we'll start with DI and we start with our instrument model. MWA tile is made of a 4x4 grid of dipole antennas. Those are connected to a beamformer that applies analog delays through various delay line switches to be able to point in a particular direction. Now, if a camel has gone and squashed one of those dipoles and we've turned it off, that does actually change the beam shape a little bit, and we do need to account for that. There are a fixed number of azimuth elevation coordinates that we can point the MWA to, and the advantage of that is that every possible beam can be very accurately simulated, and that whole simulation, once it's compressed, can take up only a few hundred megabytes, so it's quite feasible to share around your FE, your beam simulations. And so that brings us to Hyperbeam, Hyperdrive's beam engine. There are two beam options. You've got the fully embedded element beam that was March and Sokolowski used the FECO simulation to be able to simulate this beam. And it takes into account things like dipole mutual coupling, and is our most accurate beam model anyone's made. There is also an alternative analytic beam because there is a bit of an uncommon configuration where we can kind of strap together 4 MWA tiles, and that hasn't been modeled in FEE, so we use the analytic beam for that one. And it does run really fast on the GPU using CUDA and HIP. But you don't need a GPU, of course. You can run it on the CPU as well, and you can run it in Python, C, and Rust. So one of the main strengths of Hyperdrive and Hyperbeam, I mean, is the fact that the spherical harmonic coefficients are very easy to decode on a GPU. You can put the coefficients into texture memory and calculate the beam in hundreds of millions of directions on a GPU in just a fraction of a second. So yeah, it can be really, really fast. So once you've got your nice, accurate instrument model, then you go into the direction independent calibration. So in this work, we've just used AntSol or MitchCal. It goes by a lot of different names. So you've got your data and you've got your model, and you iteratively solve for this gain Jones matrix G. We don't put any constraints on the Jones matrix. We let the leakage terms and everything fall out of it. So that's the equation there. We'd like to add spectral regularization to this, but at the moment it does a pretty good job in itself. Now we can talk about some direction-dependent effects. So the ionosphere is obviously a big problem, especially at low frequencies. It causes phase and amplitude distortions, and those depend on what direction you're looking at, which is what makes it quite difficult. So they change as well over time. They can, every couple of seconds, you would typically need to adjust for the ionosphere in a different way. And that, of course, gets worse as you go to lower frequencies. But luckily, the MWA is small enough, relatively, to make use of a nice heuristic because it's less than 6 kilometers. The ionosphere is typically, hundreds of kilometers up. So we can basically assume that all baselines see basically the same ionosphere, and we can that kind of helps things. So in the literature, we refer to that as Lonsdale Region 3. And so this is just a diagram of the position offset calculation. So the angle that a source is deflected is calculated by that formula there, and it depends on the slant total electron gradient. So basically, the gradient of the total electron content. And it is proportional to lambda squared, the wavelength squared. So yeah, light travels through regions as light travels through regions of different electron density, it gets refracted. And the angle is the opposite direction of the increasing total electron content. And so, yeah, in order to fit those offsets, we have to do that per source. So we start off by subtracting all other sources in the sky as good as we can. We phase to the actual position of the calibrator that we're looking at. We average across time and frequency to reduce the contribution from other sources in the sky. And then we fit constants of proportionality, so alpha and beta, that tell us how much the source has been deflected in the L and M directions, the direction cosines, with lambda squared. Yeah, but there's a bit of a problem. So if you don't treat this, if you don't do these things correctly, you can lead to the position offsets kind of diverging and going off into infinity. So first of all, you got to make sure that your sky model is complete and accurate, so that you're subtracting your sources correctly. We subtract in the descending order of brightness. We downweight any short baselines because they're not really contributing much to our point source model. We fit an additional parameter in addition to alpha and beta. We fit just a scalar gain G that helps us get the subtraction more accurately. And in the future, what we'd like to do is be able to DI calibrate towards the few brightest sources, but this is quite expensive and complicated. But the other tip is to limit the rate of convergence, because sometimes this is the input to your subtraction. If things go wrong, then things will tend to go off into infinity. So you want to kind of go in baby steps, and then that's as you loop over the entire model multiple times, you'll be able to get more accurate solutions each iteration. And you want to make sure that you check for any diverging solutions and reject them so that they can be picked up in the next pass. So I'll talk about some of the projects that use Hyperdrive. GleamX has just swapped over to using Hyperdrive, and as well as Beely. So they typically use about 250 sources. And there's a little trick that they've got where they DI calibrate the start and the end of the observation. And if those solutions are changing too quickly, that's a pretty good heuristic that there's something going on in the ionosphere or something's wrong. And they're able to reject or avoid those observations without having to go into slightly more expensive direction-dependent calibration. They can kind of tell that these observations are just not worth using and they can skip them. But the epoch of reionization is really what Hyperdrive was built for. And unfortunately, you would have just missed Redeeming Anarchy's talk that was this morning. But there was a lot of things that went into that for quality analysis to be able to select which observations were the best ones. But in that work, in the 2024 paper, we directly compared Hyperdrive and RTS, and it does look, pretty neck and neck, but Hyperdrive does come up with some advantages. And the limit that we were able to produce, I won't get into one-dimension power spectra estimates, but basically the summary is you want to try and get this number as small as possible. And in one particular K-mode at one particular redshift, we were able to give the best NWA EOR limit that anyone's done, and that was 3.5 times better than the previous limit, which used the RTS. So these are the settings that we did use for that work. So we use quite a lot of sources relative to GleamX, and we ionospherically subtract 1,000 sources to give a total of 8,000 sources that we're subtracting. Another really good use case that I won't get into in detail, but please check out Shintaro Yoshira's talk today at 1:50. This is a really good detailed case study of a particular traveling ionospheric disturbance. And what they were able to do was using the Hyperdrive ionospheric offsets. These give you a lot more detail and to observe ionospheric phenomenon compared to the Roti maps that you would. So this is the GIF on the left. The offsets give you a really, really fine, detailed view of the ionosphere compared to typical methods. And we also have used it for SKA low in the SKA Data Challenge 3. This was there were some approximations, so it's not it's only simply a Stokes eye data set, and it used an airy beam approximation because it was more about focusing on subtraction techniques, not the getting into the details of the beam. But Eric Zhong over in Curtin is working on an SK-low analytic beam and is able to get calibration solutions out that are able to deal with station rotation. And that is also full drones as well, simulations using OSCAR. So that's quite promising work, but it's still in progress. So finally, the performance, if you are using a typically previously we'd use a GPU, a CPU to calibrate, but if you use a GPU, you can basically calibrate 200 times more sources in the same time that you can do on a CPU. The other takeaway from this is that RTS does have a shorter wall time, but it requires 25 GPUs to run. And when you're waiting on a supercomputer for 25 GPUs to become available, you can be waiting for quite a while. But when you're using GPUs for your DI calibration, your wall time for DI is basically negligible compared to most imaging that you would be doing. So it's on the order of a couple of minutes for most use cases, which yeah, it's basically negligible compared to imaging. And I don't have the numbers here, but roughly about an hour-ish for you to do the EOR subtraction of 1,000 sources ionospherically, and then total 8,000 sources. It takes about an hour. And finally, I'll leave you with this cool animation of what happens when a traveling ionospheric disturbance interferes with the middle of your observation. So these are all the position offsets colored by direction. And in the top right, we have the tech field that was reconstructed from those offsets. You can clearly see that there's some really, really interesting phenomena happening in the ionosphere, and you just can't see this detail with traditional rotating maps. Thanks.
Questions?
First of all, great presentation. Love the animation.
Thank you.
I just got 2 questions, if you don't mind. So talking about the software earlier, you had it saying that it would flag bad data, essentially trying to remove it. How does it flag it? How does it know that it's bad data? And what is the rate of false positives and possibly even false negatives of the software?
That's a great question, and I have lots and lots of slides on that that I've put together for radio school. So I'll go through the details with you later. Essentially, I would refer to the AOFlagger paper for how AOFlagger does it. There are the other algorithms that we use have an issue, a very big issue with overflagging that we're looking into. But AOFlagger works on a per baseline basis and is quite statistically well justified, and it's very robust and fast, and it's a great algorithm. But the other algorithms at the moment are implemented in Python. They're quite slow, but they tend to stack all the baselines together so you get better sensitivity. But that means that you are flagging baselines that maybe have no RFI in them potentially. So they do overflag, and that is something that, based on the science case that you're using, like if you're looking for things that change, if you're doing time domain stuff, you probably don't want to do the extended flagging. But if you're doing EOR, then you probably do want the quite extensive flagging. So yeah, that has a very long answer that I will chat about with you later.
Awesome. Just one more question. Out of curiosity, do you know what ionospheric effect would be this? Like if it's a weather sort of thing, is it some flux, or is it just some random event?
I did actually ask this question at a previous URSI. I showed the same animation, and someone called Lindsay, who's around, sent me an email with all the details, who's an expert on this stuff. And I can't remember the exact details, but it's called a traveling ionospheric disturbance. If anyone in the audience wants to give any more details on that, I don't know the exact nature of, it's not quite my field, yeah, but it's really cool, isn't it?
Thanks. I think we have time for more questions. I was quite surprised that for RTS, the time to run is actually kind of comparable. So is it because it's doing less?
Well, if you look at the numbers here, the RTS, for the same thing, I think it's, let's see, when you do 100 sources, it takes on the GPU 1,000 sources is 2 minutes on RTS, and with the hyperdrive on the GPU, it's around a minute. So it takes half the time on RTS takes half the time, but uses 25 times more GPUs. So per GPU, hyperdrive is much more efficient, and that allows us to process like the 267 terabytes of EOR data, because on a supercomputer you can do those DI calibrations. We do like 50 at a time. So the overall, the amount of power that was used, the overall wall time and everything is much, much better on hyperdrive if you're doing lots of DI calibrations. But RTS was designed to be real time. And so the most important factor was the wall time. And if you have 25 GPUs, you will get things done faster, but you use it's much more efficient to use hyperdrive.
Thank you. Let's thank them again. And the final talk before the coffee, the session is by Stefan Weinholz, and he will tell us about closed forms of collaboration solutions for large aperture arrays.
Thank you. I can see that, yes, that presentation of all the slides in the room. Basically, about half a year ago, I was contacted by Hausen, who had been is a signal processing researcher at ISEN, working on subspace techniques, and he found a way to solve the direction-independent calibration problem that we have in closed form. And he contacted me to see, well, does this actually work when we try to do this in practice? I mean, he made a purely theoretical derivation. So let's hit the green button, see what happens. We call this the calibration of large arrays by subspaces. And I'll, in this talk, I give obviously an overview of the algorithm and the idea behind the algorithm, show you some examples on LoFA data, and also show you some of the constraints of this algorithm. So the basic idea is that if you have a covariance matrix, so this is for a single snapshot in time or frequency, can be integrated obviously, so you can store the visibilities in a covariance matrix, which I call R. And the basic idea is that if you have purely noise on the autocorrelations, and you multiply this by the diagonal matrix, and the inverse of the same diagonal matrix afterwards, so this second term, dr d minus 1, you completely filter out the autocorrelations. We define this delta R to filter out the autocorrelation powers. And if you then expand the model for your visibilities in the case of direction independent calibration, you get a diagonal matrix with your G's. You get two matrices actually with the Fourier kernel. Basically, we assume that for calibration, the sky consists of a number of discrete sources. So you can define a Fourier kernel mapping each source onto all the visibilities. You basically get your source powers and a kind of negative image due to the subtraction of the filtered model. So that's basically on the second line, the data model for delta R. And an interesting bit is that if the inverse of this derivative t is actually the same as its Hermitian transpose, which is true if you build a diagonal with phasors, then yeah, delta R is also a Hermitian matrix, and you can exploit that property to basically find the gains by finding the gains as being orthogonal to the noise subspace, which is a known subspace technique. Well, if you have established the gains in that way, and it's important to note that in this this system of equations you need to solve to obtain G, the source powers, which are also assumed to be unknown, to account, for example, for a little bit of scintillation, or in other inaccuracies in your source model. So you really only need to know the source positions. Then, since the source powers are not in that equation, you can estimate the gains without knowing the source of noise powers, and therefore you can start working backwards to determine those parameters as well. So we thought, well, let's try this on the AP-RASC system, which is a piggyback system on the LOFAR telescope. It is called the Amsterdam Astral Radio Transient Facility and Analysis Center, a whole mouthful. But what it does is it basically allows us to make a copy over a limited bandwidth of the raw voltage data of all individual dipoles in the inner 12 LOFAR station. Feed that into a correlator, and basically do all sky monitoring at a 1 second cadence. For this experiment, for this test, we use the inner 6 LOFAR station, of which you see an aerial photograph on the bottom left, and on the right you see the array configuration. You may notice that the antennas in one station are marked with red dots, and that is because we decided to try how well does the algorithm work for data for a single LOFAR station, and how well does it work for the larger configuration of 6 stations, but basically as a superstation, because we did have access to the individual signals. So what is important here, and that's because it is a subspace technique, so ideally you would like to be able to see a distinction between what we call the signal subspace, so the eigenvectors representing the actual sources in your data, and the noise subspace. And if you follow the red circles, which represents the eigenvalue structure of the visibility matrix for the single station, you will see that there is a very smooth transition from the signal subspace to the noise subspace, which is basically caused by the lot of diffuse emission of the electric plane, because in a single station, you have many short baselines, and all these baselines are sensitive to this large bit of diffuse emissions. This is not what you want to see in a subspace technique, because you want to be able to make this distinction between what's noise subspace and what's signal subspace. So actually, when we tried the algorithm on a single station, it didn't perform that well. But if we look at do the same experiment, so we pick the much larger covariance matrix for the cluster of 6 stations, there you see that a couple of eigenvalues very clearly stand out, basically representing the subspace spanning sources like Cassiopeia A and Cygnus A, which are really bright on the northern hemisphere. And because you have much more longer baseline in this larger configuration, the fraction of baseline sensitive to stuff like the electric plane is much less, and therefore they're not dominating anymore. And therefore you have a much clearer transition from the signal subspace to the noise subspace. And in that case, the algorithm works really nicely, which we show on the right-hand plot, showing the gain phase solutions for each of the antennas involved. So you see basically 6 clusters of stations. So you could model the delay to each of the antennas in this superstation as a delay per station plus some additional delay within the station for each of the antennas. That's basically what this phase tells you. That's why you get these jumps. Also, you see many blue dots for each antennas. And that is because initially, when we started playing with this algorithm, we did not know what is the optimal way of doing this differencing. So you can make many choices for this diagonal matrix D. So we just generated random Ds and tried running the algorithm for different values of D. We basically made show you hundreds of these estimates in these blue dots. Then we also took the median of all these blue dots for each antenna. And the nice thing is that you then get the black dots, which are very difficult to see, but they're quite in the center of this cloud of blue dots. And then the red dots represents the solutions obtained by Stefgal running on the same data. So it does show that the individual solutions for an arbitrary choice of D may be more noisy than an algorithm that's fully model-based, iterative, etc. But in the end, it converts to the same solution. So as I mentioned, initially we thought, well, how to choose D? Because you can make an arbitrary number of choices. And then it's good to know that you can also write down this first equation that you saw on the first slide differently by saying, I multiply my covariance matrix R element-wise with the difference of the matrix only filled with ones, which is basically R itself, minus basically the factorized form of this pre- and post-multiplication of these diagonal matrix. And this is actually quite an insightful equation, because suppose you have a situation where the two elements in this vector D are identical, then you will find that this difference matrix, there will be a 0 on that particular entry. And if there's a 0 in this weighting matrix, it basically means you have flagged that visibility for no reason, if assuming that your data is correct. One thing that you want to satisfy the diagonal elements of your matrix D is that the elements P and Q are not equal, because then you flag unnecessary data. Also, if you weight your data, normally you apply weighting to do, for example, inverse covariance weighting to find an optimal solution. So you normally want to assign higher weight to data with a better SNR than to data with a low SNR. If you don't have any a priori knowledge and you have an array of identical antennas, the most logical thing to assume is that all your antennas are equally sensitive, and therefore each visibility should have equal importance in your calibration. So ideally, you want this whole matrix to be have the same amplitude. That can only be achieved if there are no large differences between these values. So in the conference paper, we actually show that when you work this out, you can show that an optimal choice is that the elements of this diagonal matrix should be phasors. So for the details of that analysis, I refer you to the conference paper. So what we try to do is to basically create to start a vector of equidistant phasors along the unit circle, and then pick random permutations of that vector. So we start experimenting with that, and we also compare that to other alternative options. One option being just randomly generating phasors on the unit circle, not equispaced. Yet another option was to just pick the 4 cardinal points on the unit circle. So 1, minus 1, and minus I, and basically pick random values out of those 4 elements. and using phasers with a little bit of additive Gaussian noise, which also gives rise to some amplitude variations in the values of D. And for all these choices of D, we looked at in a Monte Carlo simulation with different noise realizations, what is the standard deviation of our solution with a certain value for a certain choice of this difference matrix. And we did indeed found that if we add additive noise, so you get amplitude differences, that then indeed your standard deviation goes up. So those are the yellow points. The other three solutions seem to be very close in performance, but when you calculate the average of all elements, you can see a very slight difference. And that is in where indeed the equi-spaced phasers give you the best result. So in terms of computational performance, and that was quite interesting. It was basically one of the first things I checked because I know that subspace techniques, because you need the eigenvectors, it's typically a cubed complexity in terms of algorithm. While of algorithms like Stefkel, they are, as Peter also mentioned, they are order p squared. Now the advantage of this algorithm is because it's a closed form solution, there are no iteration pools. It jumped from any starting point, it jumps to the right solution in one go. So there's a trade-off here, as you would expect, between number of iterations that you need versus array size. In the end, for very large arrays, the OP squared complexity will help you. But even for this aardvark array, which is already consisting of a significant number of antennas, you can already see that that it's still significantly less, say by a factor of 5 or so, than what Stefkel required to calibrate the array. There's obviously a caveat, and that is the statistical performance. So because of this weighting, which is suboptimal, because you cannot basically avoid that there is a little bit of variation in to the extent to which you weight each visibility. It means that when you run a Monte Carlo simulation with this algorithm on various noise realizations, you will find that the gain estimates produced by the class method are a bit more noisy than those produced by Stefkel. So that brings me to the summary and conclusions. We have found a closed form solution for direction independent calibration problem. So if there is no noise, this gives you the perfect solution. We've also found an optimal choice for the differencing matrix. It has quite nice computational performance, but suboptimal statistical performance. So that can either be remedied by running the algorithm multiple times with different realizations of D, but that obviously throws away the computational advantage. But in some cases, you may not actually need optimal statistical performance to get for example, if there is enough SNR and your calibration solutions are accurate enough anyway, you may not need to push that. All in all, we think this is a very nice addition to the toolbox that we have for calibrating our systems.
Questions? Anyone wants to have a coffee? I'll ask. So I think one of the good applications of anything which is closed form is that you can actually derive uncertainties. So you can look back and say, assuming that my noise is that, I can propagate errors and actually get not just gains, but gains with uncertainties. Have you thought about it?
Yes, it was we basically did a statistical analysis, so that's not probably not the thing that that you are alluding to, because we also wrote a paper about this. I referred to it in the presentation. It's in transactional antennas and transactions on aerospace and electronic engineering. And one of the review questions was indeed, so how does this respond to noise? So we did basically made a perturbation analysis there, very short derivation about an error matrix on top of your visibilities. What you're alluding is probably more deterministic effects that you are aware of, like a model mismatch. And yes, indeed, those can be analyzed, but perhaps not in closed form. Because these, it is based, subspace techniques are based on the eigenvectors, and in many cases you cannot calculate the eigenvectors in closed form. But I am aware of some cases where that's possible.
Yeah, could you go back? Really good talk, by the way. Could you go back to the eigenspectrum that you had a second ago?
Yes. How do I go back? Like this.
No.
Yeah,
that's the one. Forward. Yep. So that gentle slope, I've seen that before, and I spoke to Greg Helborg, and he said there was a reason for it, but I don't remember what it was. And is the difference between the red and crosses?
Yes. Yeah. So actually, the whole story is more complicated as usual. But suppose you have you would correlate pure noise from all antennas. So your covariance matrix basically it is a measurement of purely uncorrelated noise. And there are quite a couple of papers from in statistics. But the eigenvalue structure of such matrix looks like, and it's indeed shows you the first eigenvalue is up slightly, then it follows like almost like a slope, and then the last eigenvalue drops a little bit further. So this typical S shape is in there when there are pure noise. So what changes if I start adding sources? In this case, there is also the galactic plane, the diffusion emission involved. So what happens?
Is that on the bit at the end? That's basically this pattern that's coming from the pure noise, and then it's what it say the eigenvalues up to say the 10th one, there you start seeing it goes up faster than what you would expect for pure noise, because that's where the diffusion emission kicks in. And then, the first eigenvalue, really can be associated to a source like SCPA. So then that's one more not push. So basically, it's a nice example of superposition, basically.
Thanks. I guess we're running out of time, so let's thank Stefan again. And we'll reconvene after lunch for this session, but I guess we'll have a general lecture. And the coffee break. Thank you.